Now we're going to move on to page 14. So if you wanted to go ahead and try these by yourself and then watch the video to see if you're correct, I suggest that. If you want to follow along, let me do one and then you try a couple by yourself. That works too, but you need to get in the habit of trying these problems by yourself and not just waiting for me to do them if you really want to learn what's going on. So in part number 1, we're just deciding if the following are quadratic equations. And we've talked about this a little bit. I just wanted to see what you remember. So if you want to pause the video and give these a shot by yourself, I'd use pencil. Okay, a quadratic equation, we have to have an x squared. In other words, there has to be two x's being multiplied somewhere in order for this to be a quadratic. So in number 1, we have y equals 6 to the x power. So this is not quadratic. Number 2, we have x squared, so this is. Number 3, we only have a single x, it's not squared. This one is actually linear, because you could graph a line. And then number 4 also has an x as the variable, so this is not quadratic. And we're going to talk about this later, but you might know the vocabulary that it is exponential. Okay, part 2. Determine if the following tables represent a quadratic equation. If they do, find the second difference. So all we're going to do is check and see if they have a second difference. So we're going to count our x's, see what they go up by. So 3 to 4 is a plus 1, 4 to 5 is a plus 1, 5 to 6 is a plus 1, 6 to 7, and 7 to 8, they all increase by 1. Now, if you can't figure out what we're adding to move down, you can always subtract backwards. So like 110 minus 90, there's a difference of 20. 90 to 72, there's a difference of 18, but it would be positive because to go from 17 to 90, it's a plus 18. To go from 30 to 42, moving back up the table, is a 12. 42 to 56 is a 14. And then here, 56 to 72 is a 16. If this first pattern was the same, it would be linear, so that we know this is not linear because these aren't the same. So we want to check for a second difference. So to go from 12 to 14, it goes up by 2. 14 to 16, it goes up by 2. 16 to 18, it goes up by 2. And 18 to 20, it also goes up by 2. So yes, this is quadratic. The second difference is 2. And I get lazy and just put second diff for difference. So I suggest you pause the video and try number 6 and number 7 by yourself. And then come back and check your answers. Okay, moving on to number 6. We're checking for a second difference. So what I do is if I notice these are all counting by 1, I just do this. If they're all counting by 1, they're fine. So from 17 to 11, it goes down by 6. 11 to 5, it goes down by 6. 5 to negative 1, down by 6. Negative 1 to negative 7, down by 6. Negative 7 to negative 13, down by 6. Negative 13 to negative 9, that goes up by 4. So there's no way that this can be quadratic, because if we take a second difference here, there's nothing changes. This was all good with a first difference pattern until down here, so this is not quadratic. Taking a look at number 7, I gotta get this to refocus. So same thing, if you want to give that a shot by yourself, you can. So again, I notice the x's are all increasing by 1, so I just do this. From negative 28 to negative 11, that goes up by 17. From negative 11 to 0, it goes up by 11. From 0 to 5, it's 5. From 5 to 4, it goes down by 1. From 4 to negative 3, it goes down by 7. From negative 3 to negative 16, it goes down by 13. So we know it's not linear, because if it was linear, there would be a first difference. So we have to check the second difference. From 17 to 11, it goes down by 6. 11 to 5, down by 6. 5 to negative 1, down by 6. Negative 1 to negative 7, down by 6. Negative 7 to negative 13, also down by 6. So this does have a second difference pattern here. So is this quadratic? Yes. Our second difference is negative 6. Okay, moving on to part 3. We're just finding the roots. So our very first step was to set this equal to 0. Your second step is to set each element equal to 0. So x minus 5 equals 0, x plus 7 equals 0. And then you're going to solve for x. So plus 5, x equals positive 5. And then subtract 7, x equals negative 7. Again, if you notice, since there's x and a number here, and then x and another number, if there is no coefficient or no number in front of x, you can just take the opposite of the number in parentheses. So see, there's a minus 5 here. Your root is a positive 5. There's a plus 7 here. So your root is a negative 7. If you don't want to remember that, then set everything equal to 0 and solve. I would pause the video and I would try number 9 and number 10 by yourself. If you remember the rule for number 9, you could straight up say that your roots are positive 3 and positive 9. How did I know that? We have a minus 3 in parentheses, so that would become a positive 3 as a root, and a minus 9 is in parentheses, that would become a positive 9 as your root. If you didn't remember, you can just set each element equal to 0, and then solve. You would add 3 to both sides, and get x equals 9. You get the same answer either way. But if you remember the rule, it does save you some work. Okay, number 10 does throw you off a little bit. Why? Because I put some coefficients here in front of the x. So the only one that you could use the rule on is this last set of parentheses, because there's not a numerical coefficient in front of x. How do you do your rule? You set this equal to 0. Sometimes I get lazy and just write that over with a 0. Split your parentheses. So we're going to have 6x plus 4 equals 0. 2x plus 3 equals 0. And I'm just going to continue with the setting to 0 rule to find the other root. So solving 6x plus 4 equals 0, I'm going to subtract 4 from both sides. I'm going to divide by 6. So right now I have x equals negative 4/6, but that's not reduced. So I'm going to divide this by 2. So I get x equals negative 2/3. Sometimes your root is going to be a fraction, and that's okay. 2x plus 3 equals 0. We're going to subtract 3 from both sides and get 2x equals negative 3. We're going to divide by 2 on both sides and get x equals negative 3/2. Finding the last one, we would just subtract 5 from both sides and get x equals negative 5. So here is what the front of page 14 should look like. Okay, flipping it over. Okay, for 11, 12, and 13, we are going to just sketch the graphs. And what I am going to do, I'm going to add a little bit here. we're going to say find the y-intercept also. We are going to find that y-intercept to help graph it. So for number 11, first thing we're going to do is find the roots. So there's no coefficient in front of x, so we can just say that x is going to be positive 5 and x is going to be negative 7. We don't have to solve this one. If you need to see how to solve it, it's the same thing as number 8. Okay, now I'm going to find the y-intercept. In order to find the y-intercept, we did it in the previous set of notes, we are going to plug 0 in for x. Because on a graph, if we're crossing the y-axis, anywhere on there is when x is 0. So we're going to have y equals, instead of the x is a 0, minus 5. Instead of the x is a 0, plus 7. 0 minus 5 is a negative 5. 0 plus 7 is 7. So this y-intercept is going to be way down at negative 35. And I'll show you how we use that in a second. So the most important thing here are these two roots, 5 and negative 7. And this doesn't have to be perfect. So I'm at negative 7 and positive 5. And how do we know which way the tails are going to go? So your A value is a positive 1, which means your graph is going to be shaped up like a cup. And we just found that your y-intercept is going to be way down here at negative 35. So all we know, it's going to look something like this. And that's all you need. You know, based on your roots, that your arrows are going to be shaped up, pointing up. And then we know our y-intercept is way down here. It's going to be U-shaped. Take a look at number 12. So before we even do anything, take a look at our A value. Our A value is negative, which tells us it's going to be shaped down like a frown. If you know the shortcut, we can just say that our roots are negative 1 and positive 2. How did I come up with that? There's no coefficient in front of the x's, so you can just take the opposite of the number in parentheses. Let's say you wanted to solve it. You would set everything equal to 0. So negative 2 equals 0, x plus 1 equals 0, x minus 2 equals 0. Well, negative 2 equals 0 makes no sense. X plus 1 equals 0. We're going to subtract 1 from both sides. Get x equals negative 1. X minus 2 equals 0. You're going to add 2 to both sides and get your positive 2. I also want to find my y-intercept. To do that, we're going to plug 0 in for x. So y equals negative 2 times 0 plus 1 times 0 minus 2, which would give us negative 2 times 1 times negative 2. And negative 2 times 1 is negative 2 times negative 2 is a positive 4. So sketching our graph. It doesn't have to be perfect. So we know that our roots are negative 1 and positive 2. We know based on that A value that our tails are going to point downward. We did find that our y-intercept was 4. 1, 2, 3, 4. So based on that, just sketching the rest, it would look something like this. And again, doesn't have to be perfect. I suggest you try number 13 all by yourself and pause the video. That way you get some good practice. Okay, if you notice in number 13, there's only one set of parentheses. This first coefficient is a negative 1, which means your graph is going to be shaped down. Set each element equal to 0, so negative x equals 0, and then x minus 3 equals 0. This is a negative x, so to get the x by itself, you divide by -1. So our first root is 0, add 3, x equals 3. So those are our two roots. We are going to find the y-intercept. So in order to do that, we're going to plug a 0 in for x. Well, -0 is just 0. So then we have 0 times -3. Well, 0 times -3 is 0. So sketching your graph. Again, doesn't have to be perfect. We do know that our roots are 0 and 3. So 0, 1, 2, 3. We know it's facing downwards. And that's all we know. And we found our y-intercept of 0, which is already plotted here. So we're just going to sketch our graph. That's simple. Okay, part number 5, describe the end behavior of each function. Super easy. If we have an odd, I'm going to write the notes over here. If we have an odd exponent, it's going to look like a line. So if the first number is positive, it would look like a line with a positive slope. If the first number is negative, it would look like a line with a negative slope. If your highest power is even, it's going to follow the same rule as the quadratics. So if it's a positive a value, it's going to be shaped up like a cup. If it's a negative a value, down like a frown. And I'm probably going to show an excessive amount of work here. You don't have to show the work. You could go right to the answer. If you think you're good, I would pause the video and try answering them by yourself, and then see if you're right when you're done. Number 14, this is a squared, so it's a quadratic. How do you know which way it's going to point? This first number is positive, so it's going to be up like a cup. So on the left-hand side, as x goes to positive infinity, how does f of x go? This left arrow also goes towards positive infinity. On the right, as x goes to, and this should be negative infinity up here. So as x goes to negative infinity, sorry for that typo. X goes to positive infinity, f of x goes to, on the right-hand side, that also goes to positive infinity. Okay, number 15. The highest power is 5, which means it's odd. Look at the number in front. There's a 1 right here. So the tails would match the line with a positive slope, because it would look something like this. 1, 2, 3, 4, 5, if you graphed it. Okay, so as x goes to negative infinity, on the left-hand side, which way does your arrow point? Again, it matches a line with a positive slope, and that arrow goes down to negative infinity. As x goes to positive infinity, which way does your arrow point? Your arrow points up towards positive infinity. Number 16. It's an odd power, so it's going to look like a line. If the first number is positive, it would have a positive slope line. If that first number is negative, it would be a negatively sloped line. So this is a -1, which means your tails would match a line with a negative slope. Okay, so filling in your end behavior as x goes to negative infinity. So as you follow your graph left, your arrow, so your f of x, goes to positive infinity. On the right-hand side, as x goes to positive infinity, your arrow, f of x, goes to, this arrow points down, negative infinity. Okay, at this point, you should feel pretty comfortable to try number 17 by yourself. It's an even power of 4, which means it's going to look like a quadratic. This is a negative number out front, so it's going to be shaped down like a frown. It would look something like this, 1, 2, 3, 4, if you actually graphed it. If you don't really care, all you need to know is which way the tails are going to point. So as x goes to negative infinity, which way do your arrows point? And as x goes to positive infinity, which way do your arrows point? So on the left-hand side, your arrow points down towards negative infinity. As x goes to positive infinity, on the right-hand side, they also point down towards negative infinity. So this is what the back of page 14 should look like. And this is what the front should look like. So make sure you have all of that copied down.